This is a video about the Laplace transform of piecewise continuous functions. So to get everybody on the same page, a piecewise function, it's a function that has different formulas for different inputs. So let me give you a couple examples. So here's one, f of t is 0 if the input t is smaller than 0, or if it's less than 0, and it's 1 if t is larger than or equal to 0. So what's the point here? I just get these horizontal lines where I get the horizontal line at 0 if t is less than 0. Notice I've got like an open circle there to indicate that I'm not plugging 0 into that part of the function. But then I get that the output is 1 if t is bigger than or equal to 0. And so that would be, of course, like the equation y equals 1, if you want to call it that. So it's kind of like we're gluing these two functions together, and this is where we're telling us maybe where to glue, around where to glue. Here's another example. G of t is let's say x if x is less than 1, and x squared if x is bigger than or equal to 1. So that should probably be an x right there instead of a t. But anyway, my point though is that you just get kind of our usual line that we like, y equals x for x values less than 1 like it says here. And then it makes this jump though where the graph turns into our favorite parabola y equals x squared if we're to the right of -1. So that would be all this stuff here. So again, piecewise functions, like I said, different formulas for different pieces. Okay, so we'll say that if each one of the pieces is continuous, so like for example, like x and x squared are both continuous, then we'd say that that is a piecewise continuous function. Now, so let me tell you about one of the more important and common piecewise functions you run into in a differential equations class. It's called the Heaviside function, where a is a constant. There's a Heaviside function for each constant a, but what it is though is it's 0 if t is less than a, and it's 1 if t is larger than or equal to a. So if you look back at my green example above, I could call that, if I wanted to, this would be like u1 of t, u0 of t. Because where does it make this change at? It happens when t equals 0, and it's just 0 if it's to the left, and it's 1 if it's to the right. So that's an example of a Heaviside function. And there's a picture of that one there, and I've tried to draw it in general, like with different values of a. You're just kind of shifting where this happens along the x-axis there. So if you're given another function though, what's interesting is to take the product of UAT with your function. Remember maybe from college algebra that this shifts your graph to the right a units if a is positive, and it'll shift it to the left a units if a is negative. But then when I multiply by the Heaviside function though, this is kind of like a switch, and we'll see in a picture in a minute, it kind of turns on the graph of this function whenever I am passed the input a. So here's an example here. If you start with the green function, square root of t minus 1 I just picked, then what would say u2 times f of t minus 2 look like? Well, what does that do? What I'm trying to say is I won't get the square root graph until I'm past the value, the input value t equals 2. So I don't get the square root looking part until I'm to the right of t equals 2. And before that, it's just 0. So that again would be the Heaviside function, what starts at 2 here, or where a is 2, times my formula, which if I plug t minus 2 into that, that's just this part right here. So like I was trying to say a second ago, it's kind of like some kind of a switch where I don't actually start doing the square root function. I don't really get the green. It doesn't come on until I get to the input 2. And that's what I'm trying to say above. So what we're interested in is what's the Laplace transform of a Heaviside function, say u(a) of t. And I've tried to put in yellow that constant a. Well, let's try to compute it. So remember, what's the definition of the Laplace transform? It's this crazy improper integral. It's not so crazy after all. But let's think about, what did this thing do again? Well, it's 0 if you're to the left of a, and it's 1 if you're at a or to the right of a. So that suggests that you should split this integral into two integrals. One that goes from 0 to a, and the other one that goes from a to infinity. Remember, you can do that with integrals. But ua is 0 if you're to the left of a, so therefore this whole integrand is 0 if you're to the left of a. So it's 0 for values from 0 to a is what I mean by that. And remember that ua of t is 1 if you're to the right of a. Well, for this integral, you're to the right of a, therefore it should just be 1 times the exponential. So I just need to figure out what the improper integral of this exponential is. And we'll write that as a limit, where the limit is just to take care of that endpoint in the top, your top limit of integration. And remember your antiderivative formula, so minus x goes underneath. Take the reciprocal of that is what I mean. And now when we plug in our values for t, so t equals n minus what you get when you plug in t equals a, looks like this. And what do we take a limit of with respect to n? Well, n's only in this one. And what do I know? I know that that piece will go to 0 as long as s is a positive number. Because if s is positive, then that guarantees me that that exponent is all negative, so it should go to 0, right? An exponential with a negative exponent goes to 0. And so all you're left with is positive e to the minus as over s. And so to recap that, the Laplace transform of the Heaviside function, where the kind of important point is a, that base, is just e to the minus as all over s. So what's the Laplace transform of one of the kind of switches? What if you took the product uat times f of t minus a? Where we're assuming that, say, this thing has a nice Laplace transform, this f. So let's try to compute that. And it's going to be kind of similar to the above. So same idea. I'm going to plug in this red function just into my definition of a Laplace transform. And what else do I know? Well, I know that this thing in some sense switches on at a, so that again suggests splitting this integral into two pieces. Now, for one piece, when we are a t value from 0 to a, I know the Heaviside function is 0, therefore that whole integrand would be 0, so that's why that 0 is right there. And on the other hand, when we are to the right of a, then I know that this Heaviside function is 1, therefore this integrand should just be the exponential times f of t minus a. So that is this from a to infinity, we're just integrating the exponential times f of t minus a. So what we're going to do is a little substitution here. We'll let u be the inside of f here, t minus a, and what you notice is that I've also got a t here, so I should make use of the fact that I could rearrange that equation right there to say that t is equal to u plus a. We'll plug that in up there. So if u is t minus a, then that tells you that du should just be dt. And let's plug all that good stuff in. Oh, by the way, too, let's see. When t is equal to a, that tells me u is equal to 0. So we're going to change this bound to 0 in the next step as well. And then one more thing, as t goes to infinity, well, that gets huge. Well, then u goes to infinity also. So this turns into the integral from 0 to infinity, e to the minus s. Remember, plug in u plus a, because that's what t is, times f of u du. We're going to use some exponent rules to split that into two pieces. And so this would be e to the minus su minus sa. And remember, we can pull that apart as this. And then, by the way, the variable you're integrating with respect to is u. Therefore, this exponential that doesn't have any u's in it, well, that's constant, so it can come out front, so it doesn't bother us when we're taking an actual integral here. And what I hope that you see is that, well, wait a minute, this just looks an awful lot like, I know I'm using u instead of a t here, but that just looks like the Laplace transform of f. And exactly that's what it is. So what do we get? What's the answer? We'll have this exponential out front times the Laplace transform of f. And so to recap that, the Laplace transform of a product of a Heaviside function times like your shifted function f should just be e to the minus sa times the Laplace transform of the f that you're dealing with.